Welcome to another topic of statics. Today I'm going to concentrate on force vectors. This is part one of a four-part series on force vectors. So today I narrow the objectives to really two main objectives here. We would discuss how to resolve a 2D vector into components. And you would learn how to add a 2D vectors using a Cartesian vector notations. An example of a conceptual presentation of what we are going to discuss today is given in this figure down below. There is a hook that is pulling on two chains. As you can see, the end of these chains could be connected into really anything, and the end of the hook would be connected to a crane. The simple question is if we start operating the crane and the hook starts moving upward to your page, what would be the forces that would be exerted on F1 and F2, and how we can actually determine the angle that these forces have with respect to one another. Again, this is pretty conceptual. We are going to shortly get into how we can actually resolve vectors into components in two dimensions, and also how we can add them. There are some activities we would go over today, including reading quiz and application and attention quiz. Again, as you have watched lecture number one, you should be familiar with some of the activities that we perform while discussing the topics. The first reading quiz is: which one of the following is a scalar quantity? Force, position, mass, or velocity. Again, we're not going to go over the answer to these. These are for you after reading the appropriate chapters of your textbook. You should be able to answer these questions. The second reading question of the quiz is for vector additions. You have to use which law? Newton's second law, the arithmetic law, Pascal's, or the parallelogram. So again, it's for you to find out, and if you have questions, please let me know. So here's an application of a vector addition as shown here. Let's assume that we are pulling some group of chains. In this case, there are three chains. They're connected into a hook. So there would be three concurrent forces acting on the hook as a result of due to the chain. But there are three of them due to the chain. So we need to determine if, as a result of the forces that are applied to the hook, if this hook will fail. Failing in this case is either due to bending or breaking of the hook itself. So we need to know what will be the resultant forces acting on the hook. There's no other way that we could determine that without knowing what will be the resultant force acting on the hook. After we determine what the resultant force is acting on the hook, then we would look at the hook itself to see if it can actually safely resist the resultant force. So to put things in perspective, let me talk a little bit about the scalar components versus vectors. please keep in mind that vectors, they have force, there are forces and examples of vectors for this class. Also, velocity is a vector. As a result, a vector has a magnitude and a direction. The rules that we use for adding vectors is what we call from mathematics parallelogram law, and the way we show vectors in order to be able to distinguish them in text. They're usually bold, and they have an arrow or a caret over them, right next to them, and different way of showing it. The most common ones is an arrow or a caret. So you can compare vectors with scalar components, for example, mass and volume. It has a magnitude, and it could be acting positive or negative, meaning that, for example, if the volume of an object shrinks, then we would give it a magnitude of negative, whereas if it expands, give it a magnitude of positive. This is just an example. It doesn't necessarily mean anything, but just to put things in perspective for you guys. So the scalar multiplication and division rules, they also apply to vectors. So please keep that in mind. And that multiplication, whether it's negative or positive, it could also change the direction of the vector itself. So let's take a closer look at parallelogram law and what do we mean by parallelogram law. So vector addition, it could be performed using the parallelogram law. Half of that parallelogram is a triangle, so this law also refers to as triangle law instead of a parallelogram law, but the parallelogram law is commonly used. So if we have vector A and B in the triangle method, the tip to tail rules applies, so the resultant would be A plus B as shown in this case. Okay, so as you can see here, for example, if we have vector A and B, if you want to add A to B instead of adding B to A, we use the tip to tail. This is B, and we would simply add A to it, and the resultant would be R B plus A. So how do we subtract a vector, and how can we actually add more than two concurrent vectors graphically? So those are interesting questions to answer. Again, these are would serve as a review to what you already know from your prerequisite, your previous classes. Resolution of a vector is breaking up the vector into components. Again, in a Cartesian, in XY, or the plane in a two-dimensional. Again, we could call it U or V, or we could call it X and Y, or what have you. So force F is given here in part A, as you can see, and we would like to resolve these two into two components. So force F is given, we would like to resolve it into two components. So what we do is we would actually draw a coordinate system, in this case U and V. It could also be X and Y, which could be the angle would be different, but in this case we are using the parallelogram rule, not the triangular rule. So this would be the force F would be the resultant of two components, and that would be projected on the sides of the parallelogram. One is F sub u, the other one is F sub v. So if we add F sub v to F sub u, we would get F as shown in part C. So that's what we really mean by a resolution of a vector, resolving it into components. And what about addition of a system of coplanar forces? If we have two or more, obviously we need to resolve the components of each vector using the x and y axis system, and then we would assign a direction and a magnitude. We use the unit vectors, I and j. I is the unit vector in the x direction, j is the unit vector in the y direction. Again, the directions are based on the x and y axis, and we use the I and j to designate x and y, but I and j are unit vectors, and they also show the direction of each component of a vector. For example, the vector v is shown here. That could be force in this case, and we would like to resolve it into the two components in the x and y direction. So in the x and y direction, it would be f sub xi plus f sub yj. Again, I would is a unit vector, shows the direction of the force as it applies, and j is the same thing, except it's in the y direction. Or we could have f prime of x. Again, in this case, we show x and y in different direction, although we turn them around, but still the angle between x and y axis remains as 90 degrees. Again, these are in the negative direction of the y in this case, and positive direction of I. If we have such a vector, depends on which quadrant it's being applied to. Again, we can pretty much continue this and apply f in a different direction, depends on which direction they're really applied, and then we give it to the I and j components accordingly, using the minus and a plus sign. So in this case, both I and j, as it indicates here, and they are in the positive direction as shown. But in this case, I is in the positive direction, but the minus f sub prime y j is in the negative direction. So if we have three vectors, v1, v2, and v3, we would like to add them, and the first thing we would like to do is we need to resolve it into different components. So F1 is going to have two components, I and j, plus some constant numbers. That's going to be shown here. So step 2 is to add all the x components together, followed by adding all the y components together, and these two would be because it's going to provide us with totals for x and y components of the resultant vector. As you can see, f1 could be resolved into f1x and f1y. F2 is resolved into f2x and f2y, and f3 is resolved into f3x and f3y, and then they are added together. So we would break each vector into components, and then we would add them. So f sub r, which is the resultant vector, is vector f1 plus vector f2 plus vector f3. f1, after we resolve it, it would be f sub 1 xi plus f sub 1 yj. That's f1. F sub 1x and f sub 1y, the positive sign right next to f sub 1 and f sub 1x and f sub 1y shows the direction of each of them. They're both in a positive direction. Then for vector f2, we would have f2y is acting in the positive direction of y, so that'd be positive, so f2yj. But f2x is acting in the negative direction, and it would be minus f sub 2xi plus f sub 3xi minus f sub 3yj. Again, depending on the sign, we want to make sure we follow the signs the way it's supposed to be. In this case, it's negative. And then what we would do is we would sum them all up. There are the components that they have I terms. It's this one, and this one, and that one. So f sub 1 xi minus f sub 2 xi plus f sub 3 xi. They would be added together. So that would be minus f sub 1 x, f sub 2 sub x plus f sub 3 xi. And the components with j have j in common. It's these three, f sub 1 y, f sub 1 yj plus f sub 2 yj minus f sub 3 yj. We add those two together, and the resultant would be f sub rx, depending on the magnitude of each of them. It would be f sub the resultant in the x direction, I plus f sub resultant in y direction, j. So that's really the bottom line of adding more than two vectors, coplanar vectors together. So we can also represent a 2D vector with a magnitude and an angle. In that case, an angle of a vector f sub r, as shown here, with respect to x-axis. Remember, keep that in mind. That is only with respect to x-axis. That would be the inverse of tangent to negative minus 1 of f sub ry divided by f sub rx. That is really nothing but taking the tangent of angle theta. In the triangle that in this particular triangle here, if we take the tangent of theta and then we inverse it, you would actually calculate theta. And f sub r itself, again, using the laws of summation, the radical, take the radical of the summation of f sub rx squared plus f sub f sub ry squared. We would easily calculate the magnitude of f sub r. So this is really a straight, simple math that you have covered in your previous classes. So let's take a look at an example. Very important to apply what we've learned here to what we've learned so far. So let's take a look at this example together. So given the three concurrent forces acting on a tent post, as it's shown here, f sub 1 vector f sub 1 is 300 Newton, f sub 2 is 450 Newton, and f sub 3 is 600 Newton. The angle of vector f2 with respect to x-axis is also provided here as 45 degrees. So given three concurrent forces acting on a tent post, we would like to find the magnitude and angle of the resultant forces acting on the tent post. So let's have a plan to attack the problem. As we've just discussed, we would resolve the forces into their x and y components. Then we would add the respective components to get the resultant force, the resultant vector, and we would find magnitude and angle from the resultant component. So let's do that. F sub 1, the zero components in the I direction, the magnitude of the x component is 0, is acting in the x direction. If you take a look at that, the reason for that is we actually set our x and y axis, our coordinate system. We set y on the y axis. As a result, the x component of f sub 1 would be 0, and simply we're going to have a j component here. So note that the units are also carried throughout solving the problem. F sub 2, let's take a look at f sub 2. Again, as I've just previously mentioned, if we take the cosine of 45 degree, that would be really, and we multiply that by the magnitude of vector F2, and that would give us the x component. And then if we would take the sine of 45 degrees and multiply it by 450, that would be the y component after we resolve f sub 2 into its x and y components. So we take the sines and cosines appropriately, do the simple multiplication, and as you can see, f sub 2 would be minus 318.2i plus 318.2 j Newton. What about for F3? We do the same thing for F3, except the ratio in this case is given instead of the angle. The ratio is a 3:4:5 ratio, so we simply use that ratio to calculate the x component to resolve F3 into the x component and y component. So the x component would be 3/5 of F3, and the y component would be 4/5 using similar triangles as shown here. If I continue this down this way, it's supposed to be actually perpendicular line. So this angle is actually 45 degrees. This one also 45 degrees. So as such, we can simply calculate the components for f sub 3. So we have already resolved f sub 1, f sub 2, and f sub 3, these three vectors into their components, and as such we should be able to, using the magnitude and direction, we should be able to calculate the resultant force. So we would sum up all the I and j components respectively. As a result, we would arrive at the resultant vector f sub r being 41.8 I plus 1098 j. So although we so far use the notation of vector f sub r in this case, as a result I need to actually calculate the angle in which this vector is acting, because a vector has a magnitude and direction. We've already calculated the magnitude of f sub r in I and j component, but now we need to calculate the angle. So In order to calculate the magnitude of F sub r, knowing the x and y components of the resultant forces, we simply take square root of summation of the two components x and y, and that would give us the resultant force F sub r. Knowing I and j, it doesn't necessarily give us direction, so we need to also calculate angle phi in this case, phi in this case, it would be an inverse of the tangent of 1098 divided by 41.80, which is 87.8 degrees. So, can you resolve a 2D vector along two directions which are not at 90 degrees to each other? Yes, but not uniquely. No, yes, uniquely. So you need to find out the answer to these conceptual quizzes. Can you resolve a 2D vector along three directions? Again, 0, 60, and 120. You need to also be able to answer that. So let's solve this problem. There are three concurrent forces acting on a bracket as shown. The x and y axis is also shown as such. The magnitude and angle of the resultant forces is what we need to determine. So the magnitude and angle of the resultant forces. Again, we would use the same procedure. We would resolve the forces into their x and y components. We would add the respective components to get the resultant forces, and we would find the magnitude and angle of the resultant forces, so we can pretty much define the resultant vector. So let's start with vector, the first vector f sub 1. And again, as you can see, we know this ratio 5 to 12 to 13. We use that to calculate the x and y components of that. And then for f sub 2, we would use the angles. They're given. Again, we work with whatever is given in the problem. In this case, the cosine and sine is given. And since the angle was given, you can use the sines and cosines. And then we would actually calculate the two components of f sub 2. For f sub 3, we use the same thing. So the resultant, now summing up all the I and j components respectively, we would get the resultant force or vector f sub r as 972.7 I plus 102.7 j Newton. So again, we use the same method to calculate the resultant force, the resultant vector, and we would calculate the angle accordingly by taking the inverse of the tangent that we did discuss previously. So the angle would be 6.03 degrees. So let's take a look at this. Resolve the f along x and y axis and write it in vector form. Again, this is for you for your own practice. We resolve f along x and y. There are four answers that are given here: A, B, C, and D. Obviously, just looking at the sign, we can right away eliminate two of the answers. So f is positive 80 multiplied by let's say an unknown, and then the next one would be minus that because the j is in the in the other direction. So right away we eliminate this problem, well, that answer and the other answer. Can you determine between these two? The only difference is between the sines and cosines. Could you determine if you resolve x and y as shown? Well, if you resolve f in x and y components using x and y coordinate system, if you resolve f into its two components, one is along x, one is along y, would you be able to find the answers? I've already given you a hint by eliminating two of the answers. And next, determine the magnitude of resultant F1 plus F2 force in Newton when F1 is given and F2 is given. You should be able to actually calculate that without really any problem. That brings me to the end of our discussions for today. Let learning continue, and make sure to follow all the quizzes and all the reading assignments that is associated with this module. And thank you for your attention, and as always, if you have any questions, feel free to contact me via the course website. Thank you.